Okay, good morning. It's time to continue with our lecture for this week. Um, I just collected your homework, so if you still have your homework with you, make sure that you submit the homework before you leave today. You're going to have a second homework assigned today. I'm going to post it this afternoon, so it will go. I need to know how much material we're going to cover in order to assign the next homework. So it'll be posted, and you will receive a message when the homework is available. Again, you're going to have a week to complete that homework. So just make sure that you start working on it early. And so we're going to continue with our discussion about the flow within a department. And remember, that's going to be our focus on this class. We are trying to design a layout, a facility. We're trying to find out the best location for the departments inside this facility. And we are trying to find tools, or we're discussing different type of tools that we can use to allocate these departments within the facility. So we talk about flow measurement and how to use flow measurement to have a better idea of the dependencies and how these departments depend on each other. So if we find a close or strong dependency between departments, then we want to try to put those departments as close as possible. So we talk about quantitative flow measurements and how to use this from-to chart to identify the strongest connection between these departments. And we covered this example. We talk about how to compute these weights when you have production quantities and you have a factor. That means that the objects that you're going to be moving have different weights in terms of the number of units that you're going to be moving and so on. And we were able to find the equivalent flow, and based on the routing for the products, we found those weights for each one of the departments. So from this table, you can see that, for instance, A and C has a 44 score, which I think is the largest one. So we will try to put those departments as close as possible. Okay? Any questions? So today we're going to continue. The next thing we're going to do is to talk about how to use qualitative information to also find these dependencies and the connections between these two or three departments. And then we're going to transition to discuss other methodologies that will give us a better idea of how to allocate this department, including algorithms. So in terms of qualitative flow, flows may be measured qualitative using the closeness relationship values developed by this person, mother, and given in this table. So this person is a researcher, like we all faculty members at universities. We also do research. So when we do research, we are trying to find better ways to solve problems. So these guys came up with this methodology to try to use qualitative information to allocate departments within a facility. So he created these values, A, E, I, O, U, X, and he did a definition to each one of them. For instance, A means that it's absolutely necessary, E especially important, I important, and so on. And using those values, he created using this pyramid structure, and using those values, we developed this methodology for finding the relationship between departments within a facility. So the values may be recorded in conjunction with the reasons for the closeness value using this relationship chart. So here we have the same information, the closest rating in this table, and then we also going to have a table with the reasons behind the closeness value. So equal to 1 means that there's a flow that is frequency of use high, and number 2 means medium, and number 3 frequency of use low. Then we have 4, 5, and 6, which is in terms of the information flow within the departments. So 4 is information flow is high, 5 information flow is medium, and 6 information flow is low. So using these values and these reasons values, we can come up with a chart like this one, in which for each one of the departments or 2 departments, we're going to identify what is the closest rating, and then below that we're going to put a reason for that. And we're going to do that for each one of the departments. So for instance, this relationship here is for directors conference group and plant manager. No, meaning that it's ordinary closeness, okay. And the reason for that is the frequency of use is here. So again, we are trying to use qualitative information to find the relationship between departments. And that's what we are trying to achieve with this methodology, using the relationship graph. And you're going to perform that for each one of the departments that you are trying to allocate within your facility. Any questions? Okay. So something that we need to clarify for this relationship chart and this methodology is the difference between relationship values U, which is unimportant, and X, which is undesirable. So 2 departments can be placed adjacent to each other with a relationship value U. But 2 departments cannot be placed adjacent to each other with a relationship value X. And the reason for that is there might be some environmental issues, or safety issues, or some facility constraints that will prevent you to put those 2 departments together. Okay, so that's the difference between these 2 scores. And then we have some steps that will help you. I think it's pretty straightforward the way you will construct this, but on the next slide, I have the steps. So you're going to first list all the departments on the relationship chart. Then, in order to gather information of the relationships that are going to be happening within these departments, you need to conduct interviews or surveys with persons from each department listed on the relationship chart, and with the management responsible for all departments. So You may come up with the chart that is making sense to you, but not necessarily is what's really happening within the facility. So that's why you need to get more information from these people actually working in this department. Define the criteria for assigning close-knit relationships and itemize and record the criteria as the reasons for relationship values on the relationship chart. So that's basically addressing this part here. So you might need to come up with some type of strategy or that will tell you if these two departments satisfy these constraints, then I'm going to assign this score. If these two departments satisfy this constraint, then I'm going to assign this score. So you keep the score as clear as possible so you can be fair for all the relationships. And then establish the relationship value and the reason for the value for all the departments. And after you're done with your chart, then you're going to share that with the people who are managing the department to get some feedback. And then you might need to do some revisions based on that feedback. Any questions? So again, our goal with these tools is to try to find what are the relationships within the department so you can try to have a better idea of how to allocate these departments within the facility. And we're going to come up with better algorithms as we progress with the lecture. So the next topic on this lecture, and I'm going to touch this just a little bit because we're going to come back to this topic later in the semester, is space relationships. So the most difficult determination in facilities planning is the amount of space in the facility. Okay, so you need to plan up how you're going to allocate that space within your facility. The facilities planning or planner then has the difficult task of projecting true space requirement for the uncertain future. So you're going to have to have an idea of what's going to happen in the future in your company, at least in the areas in which you're trying to plan for your facility. Because if you provide a layout that is too strict, and don't give any flexibility to future accommodations, then that might create trouble in the future. So you need to plan taking into account what might happen in the future. In manufacturing and office environments, space requirements should be determined first for individual workstations. So, for instance, I was an intern for a bank, it's Scotiabank, when I was an undergrad, and we're trying to plan for a service department. These are the departments that basically are answering the phone calls for the clients, answering questions, and so on. And we have a space already assigned for this service department, and we needed to plan how many people can we fit in this area. So the first thing we need to know is the size of the workstations for each one of the individuals. Departmental requirements should be determined based on the collection of workstations in the department. So once you know the size of the workstations, you have a better idea how many people you're going to fit in that area, then you can plan for the department. A workstation includes space for equipment, materials, and personnel. And here we have a design of a workstation with the dimensions. So we have a mill machine, and then we have materials, and we have a lot of space because we need to move these materials into this area. Then we also have a workbench for the employee. So all those things are included in just one workstation. Okay, so this workstation will be part of the department. So once the space requirements for the workstations are determined, the space requirements for each department can be established. So you need to make sure that the operational interference are not created by simply combining the individual stations that you're going to need for that department. Additional space is required within each department for material handling, within the department, and those are the aisles. So here I have some allowances estimated based on the type of load that you're going to be moving between your departments. These are the size allowance percentage for the department. So for less than 6 feet square, then you're going to need an aisle allowance percentage between 5 and 10%, and so on. And again, we're going to come back to space requirements later in the semester, but what we are trying to achieve now with these lectures is to give you an idea of the tools that you can use to find the relationship between departments and how to allocate those departments within the facility. So that concludes the second part of the second lecture, in which we discuss the activity relationship and the space requirements. Now we're going to transition to the next set of slides, which basically it's going on the same direction, trying to find good algorithms to allocate the departments within the facility. So this third lecture is layout planning models and design algorithms. So now instead of using these qualitative measurements and trying to find out the relationships and try to address how to allocate the departments using just those scores, now we have some algorithms that we're trying to use to allocate departments, and these are going to try to optimize some type of measurement that you are trying to minimize or maximize within your facility. So something that you need to know is that the information that we're going to discuss is discussed in chapter 6 of your textbook. So now we are moving from chapter 3 to chapter 6. Okay, so topics that we are discussing, I'm trying to find the best way to align them throughout the semester. It's not necessarily going to follow the book order. Okay, so this is material from chapter 6. And in terms of the objectives for the class, we are now talking about objective number 2, their formulation models and analytical procedures for the study of facilities layout planning. Okay, so the agenda for this lecture, we're going to talk about or review the basic layout types because we need to know that information to move to the next step. Layout procedures, and then talk about one algorithm in particular. On the next lecture, we're going to add more algorithms to this list, but we're going to start with one, which I think is the easiest one, and then we're going to add to that list next week. So, the learning objectives for this lecture: understand the interactions between layout planning models and design algorithms as they relate to facilities planning. Okay, so a brief intro to this topic. So as I've been mentioning over and over again, our objective is to find the best design for this layout within the facility. So the generation of layout alternatives is critical. It's a critical step in the facilities planning process. The layout selected will serve to establish the physical relationship between activities. So on a separate note, why would someone will come to class just to sign the attendance sheet and then just leave? I mean, I'm not gonna give you a grade for the attendance. So you come to class at 8 in the morning and then sign and leave. Doesn't make any sense. So I mean, I'm looking at all of you from here. I know what's happening in the classroom, so make sure that I take his name from the list, but don't do that. I mean, it's you think I'm not seeing, but yeah, I'll notice everything you do. So, so going back to this, most facility layouts can be viewed at 2 levels. The first one is the block layout, which shows the location, shape, and size of each planning department. And then the second one, the detail layout, which shows the exact location of all equipment, workbenches, and storage areas within each department. Our focus in this class is primarily on quantitative method for developing and evaluating alternative block layouts. Why are we focusing on quantitative method? Those are the ones that we can actually agree on if we are following the same strategy. qualitative methods will depend a lot from the person doing the analysis. So so that's why we're going to focus on the quantitative methods. And before we start discussing those, we need to review what are the basic layout types. So anyone remember what are those? There's four of them. And I think on Monday I show you 4 different flowcharts that listed all of them. So without looking at your notes, anyone remember? There's one, right? Product, design, product family, departments, process department. So let me list them here. Fix, material, location departments, production line, departments, product family, departments, and process. And that could be a good question for the exam. So if you want to just highlight that. Identifying the right number and types of departments that are going to use to populate the layout is the key step for facilities planner, and that's what you need to perform first. So, you need to identify the type of departments that you're going to have within your facility and the number of departments that you're going to have, and that's your first step or your key step to start planning for the design. Okay, so now let's talk about procedures. So there's a lot of literature, a lot of I say software already programmed for trying to solve this type of problem. And software alternatives, basically what they do is they use one of the algorithms of the list that I'm going to show in a few minutes. So there are some software packages already with these algorithms embedded in that. So there's different procedures to do this to try to solve this problem. They can be classified in 2 main categories. The first one is the construction type and the improvement type. And the difference between them is very clear. For the construction type, you're going to start with a facility that has nothing in it, and you're trying to create that facility from scratch. And then for the improvement type, you have already some departments in the facility, and you're trying to improve your design based on that. So construction layout methods basically involve developing a new facility layout from scratch, and improvement Generate layout alternatives by seeking improvement in an existing facility. So next I'm going to show you 3 different procedures for layout. The first one, this is from Apple. Apples. And these are the steps they follow to plan a layout. So as you can see, there are a lot of steps. You start with getting the basic data, analyze that data, so you can analyze that using one of the quantitative or qualitative methodologies that we explained. Design the productive process, plan the material flow pattern, consider the general material handling plan, calculate equipment requirement, plan the individual workstations, and so on. So you can read through this. You don't need to memorize this for the exam. I'm just giving you an example here. Different companies might have different ways to do this type of planning. So this is another one. This is an engineer, last name Reeds, which also generated a different methodology for layout process procedures. So this is Reeds plan layout procedure. Analyze the product or products to be produced, determine the process required to manufacture the product, prepare layout planning charts, determine the workstations, analyze the storage area, establish minimum aisle width or requirement, establish the office requirements, consider the personal facilities and service, including restrooms and so on, survey plan services, and provide for future expansion. But for this particular way of planning a layout, the layout planning chart is the most important single phase of the entire layout process. And I'm going to show you the layout planning chart on the next slide. This chart incorporates the following information: flow process, including the operation, transportation, storage, and inspection of the products, the standard time for each operation, the machine selection and balance, and the material handling equipment. So here's an example. If you see this chart in one of your courses, in production planning, but if not, this is a layout planning chart in which you have the details in terms of the methods for that particular product. So fields in store, transport to temporary store, pattern making, and so on. And then you're going to list the method, so if it's a manual operation or not, and then you use this symbol to identify if that step is an operation, transportation, inspection, delay, or start. And based on that, you come up with the process for producing your product. Also, you have more information about distance for transportation, the time it takes to complete an operation or transportation step, and so on. So for Reed's methodology, this layout planning chart is essential. On the next slide is a third procedure that is called the Systematic Layout Planning Procedure, or SLP. And this also was developed by a very well-known industrial engineer called Richard Walter, and we We mentioned him already in this lecture. This framework is use activity relationship diagrams as the foundation activity. So here's the systematic layout planning procedure. On this flowchart, I'm showing you the relationship between the steps. So you start with the input data and activities, and based on the input data and an understanding of the roles and relationship between activities, a material flow analysis or from to chart and an activity relationship analysis, and this is an activity relationship chart, are performed. So you get the input data from your facility and the activities, and then based on that information, you're going to generate an material flow analysis using a from-to chart, or an activity relationship analysis using an activity relationship chart. So these are these two blocks here. So I'm showing you here the activity relationship chart one more time. So you're going to list all the departments for your facility, and then you're going to start describing those relationships using this diagram. The flow to chart is the chart that we developed in our quest last time. That's the from to chart. So using those two tools or strategies, then we can come up with a relationship diagram, which is the next step. And this looks like a network model. You basically have the nodes representing the departments, and you're going to connect those departments with relationships within your facility. So the relationship diagram positions activities spatially, and proximities are used to reflect the relationship between pairs of activities. So from here, we make this relationship diagram, and then we're going to gather information about the space and the space requirement for each one of the departments. And the next step is the space relationship diagram, which looks like the previous graph, but now we have some blocks representing each one of the departments, and with some areas, which is the space that each department is going to occupy within your facility. So the space relationship diagram involves the determination of the amount of space to be assigned to each activity. So for this step, then we're going to gather more information about, to show this information to the people managing the department. You might do some modifications. You're going to learn about the practical limitations of your design. And using that information, that feedback, you will come up with different type of alternatives for your layout. So these are alternative block layouts. They all occupy the same area, but as you can see, they have different locations for the departments. So based on modifying considerations and practical limitations, a number of layout alternatives are developed and evaluated. And then the preferred alternative is then identified and recommended. Okay, so that's the evaluation step. You're going to look at your different alternatives and you're going to find out which one is the best. But right now we don't have a way to determine, based on the allocation of the departments, which layout will be better. So right now we are trying to allocate the departments based on the relationships using qualitative and quantitative information. And we gather that information and we are able to come up with these three designs. But from these three designs, now we want to find out which one is the best. So we have multiple alternatives, but we don't know which one is the best. So that's why we need to find out ways to make those decisions. And then that's when the algorithms approaches come into place. So we're going to use these algorithms to be able to identify which design is the best. So the layout procedures presented in the previous section provide a framework to construct or improve a layout, but they do not provide a formal procedure or algorithm for some of the critical steps with associated with layout design and evaluation. The models and algorithms we are going to present in this section provide us with objective criteria to facilitate the evaluation of several layout alternatives that emerge in the process. So now we have 2 or 3 alternatives and we want to find which one is the best. And that's why we're going to use these algorithms. Any questions? So most of the layout algorithms can be classified according to the type of input data they require. So including qualitative, flow data, quantitative flow data, and some of the algorithms accepts both relationship chart and from to chart. So some of the algorithms will use the relationship chart and the from to chart as an input for finding the best design. So I'm talking about algorithms here, and I don't know if you are really sure of what is an algorithm. Any idea of what an algorithm is? Yes, sir. Yes. Exactly. So it's a set of steps in an order, in a sequence that will allow you to, based on a performance measure, to find the best decision. Okay, so it's a set of steps that you're going to follow. These steps are going to trying to optimize an objective. Let's say you're trying to maximize the profit. So those steps should guide you to, at the end, you get the solution that's going to give you the best profit, for instance. So that's an algorithm. So we can classify layout algorithms according to their objective function. So some of them will minimize the sum of flow times distances, and some of them will maximize an adjacent score. So I know most of you are from manufacturing engineering. Are you guys, do you have to take the course IE 3340, Operation Research? No, you don't have to take that one. Okay, because this type of formulation is discussed in that class. So essentially, what we do, what we're trying to illustrate here is mathematically how to represent minimizing the sum of the flow time distances. So that's what we're trying to do with this expression. We're trying to minimize the sum of the flow time distances. So we're going to have the information about the number of departments. So we're going to look at each department. We have information about the flow from department I to department J. We have the cost of moving a unit, and we have the distance. So once we sum the information for all the relationships, we want to minimize the score. So we want to find out for all the alternatives, once you test all the alternatives, which one will give you the minimum cost. Now, the second bullet is related to the other one. That one is trying to maximize the adjacent score. And here we have just the flow information and the score for the department, or for the relationship between those two departments. So these are qualitative measurements. And we are trying to find out what's the design that will give you the highest score, because that means that you're going to have the departments that have more information flow or more relationship together. So that's why we are trying to represent here with this two models. We are just illustrating mathematically those two bullets. Any questions? So here's a list of the algorithms approaches that are currently available. There's one called pairwise exchange method, graph-based method, craft, mcraft, logplan, MIP, logic, and multiple. And the ones in red are the ones that we are going to cover in class. I might change my decision in terms of this one because if you're not familiar with operation research, you might not be able to follow on that one. But I'll think about it. But for now, let's focus on the first one in red, the graph-based method. And that's the algorithm that we're going to cover today. And that's the last thing we're going to do for this lecture. So we're going to focus on the first one, the graph-based method. This algorithm is a construction type algorithm. So we are assuming that we don't have any departments in our facility already. And it uses the adjacency-based objective function. So we are trying to maximize the relationships between the departments. So this bullet basically is saying that we are going to use this. The score does not account for distance, nor does it account for relationships other than those between adjacent departments. Dimensional specifications of departments are not considered. The length of the common boundaries between adjacent departments are not considered. The arcs that not intersect this property of graph is called planarity. And the score is very sensitive to the assignment of numerical weights in the relationship chart. So here's an example. Consider a company that wants to develop a layout for its new 5 departments facility of equal size. So we're going to have 5 new departments of equal size, and we have this relationship chart. We can create a relationship diagram based on that information. So it's basically create this network diagram based on the information provided here. So we're going to have 5 departments, 1, 2, 3, 4, 5. And using the scores that were placed in the relationship chart, we're going to create some arcs. So from 1 to 2, we have 9. From 1 to 3, we have 8. Just this one. From 1 to 4, we have 10. And from 1 to 5, we have 0. Then from 2 to 3, we have 12. From 2 to 4, 13. And from 2 to 5, 7. Then from 3 to 4, we have 20. From 3 to 5, we have 0. And from 4 to 5, we have 2. So this is our relationship diagram. It's coming from the relationship graph. So our first step is to, from the relationship chart, is to select a department pair with the largest weight. If you look at the graph at the top, the one that has the largest weight is this one. So that's our first step. So departments 3 and 4 are selected to enter the graph. Step number 2, select the third department to enter. The third department is selected based on the sum of the weights with respect to the departments 3 and 4. So we already have 3 and 4 that are going to be part of our facility. And now we're going to look at 1, 2, and 5 with respect to 3 and 4. And we're going to look at the weights, the total weights for those three departments with respect to 3 and 4. So from 1 to 3, we have a weight of 8. And from 1 to 4, we have a weight of 10. Which means that we have a total weight of 18. From 2 to 3, we have a weight of 12. And from 2 to 4, we have a weight of 13. So this makes total 25. And from 5 to 3, we have 0. And from 5 to 2, we have 7. I'm sorry, it's 5 to 4, it's 2. So the total is 2. So we're going to choose department number 2 because it's the one that has the largest weight. So this one is the best. So we're going to start putting that information into a network chart. So we have 2 departments already, which are 3 and 4. And the relationship is 20. And then we're going to add 2. And 30. And we're going to proceed in the same way for the next. So we're going to pick the 4 department to enter by evaluating the value of adding one of the unassigned departments represented by a node on a face of the graph. So step 3, now we have 1 and 5. And 2, 3, and 4. And we have the total. So from 1 to 2 we have 9. 1 to 3 we have 8. And from 1 to 4 we have 10. So that gives us a total of 27. From 5 to 2 we have 7. 5 to 3 we have 0. And from 5 to 4 we have 2. Giving us a total of 9. So this one is the best. So department 1 is chosen. with a value of 27. So we're gonna put that one here. 3, 4, and 2, and then 1, 12, 13, 20, 9, 8, and 10. And then step 4 is to determine on which phase to insert the last department. So we're going to look at 5 with respect to 1, 2, 3, and 4. So 0, 7, 0, 2. So for 1, 2, and 3, we have a total of 7. From 1, 2, and 4, we have a total of 9. 1, 3, and 4, we have a total of 2. For 2, 3, and 4, we have a 9. So we are looking at all the possible combinations for that one, for the last one, and we show that these two are the best. So we want to put that node in one of those two locations, between 1, 2, and 4, or between 2, 3, and 4. So we are going to place that. We have 1, 2, 4. We have 1. And then we're going to place that one in between this triangle. So remember, the arcs cannot intersect. So we have 12, 8, 9, 13, 20, 10, 7, and 2. And the way that we're going to make this also true, 2, 3, and 4, is by adding another arc here. So we have some connection between those two, but that arc is going to be 0. And this is giving us a placement for those departments. And now we can play with that network to try to allocate the space within our facility. So we can construct a corresponding block layout based on that locations of facility. Okay, so this is our first algorithm. It's called the graph-based method. Any questions? Yes, sir.
I was just wondering, when you do this kind of process, and you start with the highest values and you push them further and further from each other, do they effectively become values that not as high? Because you're saying like this value, the high value is kind of like low.
Oh yeah, but then what you're trying to do here is that you have a certain way of communicating between the departments. So as long as you have, again, this is based on qualitative measurement. So as long as you have some type of connection between those departments, then that weight is still real. Yeah.
I didn't know just by spreading everything out more.
No, in this case,
3 and 4 are.
No, as long as you have some type of communication port, this is still valid. Still the value. Yes, sir. One and four. Yes, basically, because now you have that connection go to this department. Yeah. Any other questions? Okay, so I'll stop here and then we're going to continue on Monday. Where's the attendance sheet?